back in the days before credit cards, there were still mechanisms to track credit and debit of people, specifically for obviously buying a house. There's still mortgages. There's ways for you to buy a couch or furniture without having to spend it all up front. And the way that they did that was similar to the way we use credit cards today. It's on credit, but they used something called a ledger. And so if you went to a shop, like I can't think of any furniture stores off the top of my head now, but if you went to a furniture store and you bought a couch for $1,000 back then and you didn't have $1,000 cash to spend, you could say, hey, I'm going to buy this couch, but I owe you $1,000. And you would write yourself down on that ledger and you give them your contact information. If you needed to provide some form of legal collateral by saying, I sign away my organs if I don't pay it, then you could do that there. But the idea behind this is there is written proof that there's a transaction that has happened where you still owe them money. And then over the course of a few weeks or a few months, you would make payments to it until all of a sudden it's back down to zero and you no longer owe them any money and you come off that ledger. This is how credit works today with credit cards, although it's a lot more sophisticated with magnetic strips on plastic cards and the internet. But the idea remains the same. You borrow money from somebody, and over some time you pay it off. Usually nowadays, if you're buying small things like meals, you'll spend $5 at McDonald's on your credit card, and then at the end of the month, you'd pay that $5 back to the Visa or whoever your credit card provider is. But the idea behind it remains the same. There's a ledger that shows transactions and shows how much money you owe somebody or how much money you've paid somebody else. That's exactly what Bitcoin is, and that's exactly how blockchain works. Blockchain is not specific to monetary transactions, but the idea behind it is really is a really good thing to learn using money because it's the primary use case right now. And so for blockchain, there's a ledger. And in this ledger, it contains transactions. Now, it's a little bit less specific to it. There's no actual money or physical goods transferring on this ledger. There's nothing written like Eric bought drugs and he owes Joe $50 for it. It just says Eric put $50 worth of, let's say, Bitcoin into Joe's account. And the way that works is it says Eric puts money into Joe's account. And we're going to say $50 into Joe's. And then that does another thing. It could be like Joe paid Susan $20 for lunch or something. But it doesn't say for what. It just says the transactions. And it goes on and on and on. This is identical to the way that credit cards work. And it's identical to the way that credit worked back in the day. But the difference is that when Visa has their ledger, so Visa's ledger over here with that whole stuff, this is Visa. It's private. You can't see it. You have to trust Visa to manage your money and manage your debts and credits properly. They could theoretically invent transactions for you, and you have no way to defend yourself without pulling out all the receipts and without going to court and fighting it. The idea behind that is, the government backs Visa and big banks back credit cards and back the way that the whole monetary economic system works. And so in theory, it's fairly well protected, but there's trust involved. And what Bitcoin does and what blockchain does is it removes that need for trust. It makes this ledger public, and it allows anybody to write to it. And that poses a problem at first, because now if anybody can write to this ledger and anybody can read it, somebody can forge my name and say, Eric owes me $1 million. And now I owe somebody $1 million. And so either this ledger is no longer valuable because there's junk data on it, or this ledger has to have mechanisms in place to prevent this. And that's exactly what it does. This ledger works identically to Visa and those back in the days credit ledgers, but the key difference is I am the only person that can give somebody else money. Even though this ledger is public, I am the only person that can write my name on it. And the way that works is it's cryptographically complex, but I'm going to try to break it down for you. The idea behind it is cryptography and encryption, and the way that this really complicated mathematical and programmatic stuff works makes it possible for me to make sure that I'm the only person that can write my name on this ledger as giving someone else money. But anybody else can read it, and anybody else can verify that I authentically wrote my name on this ledger. So let's go through a little bit of practice here and kind of understand how encryption works at first, because that's critical. If you've ever bought a cereal box that comes with a decoder ring or something like that, where you turn the knob and it will draw a decoder ring here, and there's like this little knob, and there's a bunch of letters on here, and this is like hovering over Z, and down here it's hovering over numbers and stuff. And if you turn the knob, it moves the letters back and forth, and they correlate to a different letter, and you can translate your message like, "Hi, Eric," to like 7, 8, and then like 5. I don't know what this number is, 20, that's not 20. We'll say like 12, 15, 26. I mean, the idea behind it is this string can be encoded this way. And so without that decoder, you can't reverse it, right? This is impossible unless you know the decoding strategy or unless you're trying to crack the encryption. This is what's known as two-way encryption. If I know the decoding, I can convert it back to "Hi, Eric," and I can see the original message, and we're all good. This two-way encryption is something that's commonly used today in the internet. It's something called SSL. It stands for Secure Socket Layer. And it's oftentimes, every time you see a website that says HTTPS in front of it, it means that S says it's using Secure Socket Layer. It's using SSL encryption. And what this does is if you send a message to that website, like you send your forum post or your username and password or whatever, it's packaged and encrypted in a way that only the person receiving it can decrypt it. And in fact, you can't even decrypt it. You can encrypt it, but you can't decrypt it. So it's a little bit more unique in the way that this path can happen still, but this can never happen, even if you are the one that made that happen. The only person that can change it is the recipient. So that's two-way encryption. But now let's talk about one-way hashing, which is a different cryptographic function, but it's similar. Two-way encryption is really helpful if the recipient of the data needs to be able to read what you wrote. One-way hashing is really helpful if they don't need to be able to read what they wrote, but they need to verify that you wrote is exactly what you entered at a different time, or they need to be, basically it's used for verification. I didn't explain that well, but one-way hashing is really helpful for verification. So instead, let's say I typed, password is a really helpful example. So password is monkeys. And that could go through what's called a one-way hash and become a bunch of junk. It becomes like a $ and a 7 and an H, G, J, I, 6. It randomly becomes this, and in reality, it's actually much, much longer than this, but it becomes this random string of characters. One-way hashing means that it is never even possible for this to return back to monkeys. That will never happen. Doesn't matter who's the recipient, doesn't matter what. This is a destructive function that converts this into this, and this can never be reversed. So mathematically, it is impossible. Now, if you were to go through every single combination of letters in the password and run it through the exact same hashing function, you could say, oh, well, I actually accidentally stumbled upon monkeys and I happen to run into this exact same output. That's called a brute force attack. You can still figure out what this string correlates to, but requires you to go through a ludicrous amount of work. And then there's something called adding a salt here. And that actually just adds complexity. So if you add something called a salt, it's usually something that backend servers will add, and it just adds complexity. So say, for example, if I'm logging into Facebook with the same password as I'm logging into Google, if they both have different salts, my password, even if it's the same password, will have two completely different hashes on both systems. But by the way, this is what's called a hash. And it will have two completely different hashes on both systems. So if Facebook gets hacked, and the hash for my password is exposed, in theory, my password is still protected on Google because they can't reverse that hash back to my original password, and so therefore they can't log into my Google account, and they probably wouldn't be able to log into my Facebook account. But anyways, that's enough of the cryptographic stuff. But the idea is this is one way, and it's really cool in that sense that this creates this verifiable thing. Now, what is the value of this hash, by the way? If I enter my password as monkeys when I'm signing up for an account, monkeys is never stored anywhere. They don't store that in a database. They store this very complicatedly long hash. So then the next time I go to log in and I type monkeys, it goes through the same hashing function and it says, hey, is that the same hash? And if it is, it says, yep, you logged in. But if it's not, they reject me and they say you can't log in. You don't know your password. And this is a proper secure mechanism to make sure that you are storing your passwords properly. The idea here is you never store the actual password itself in the database. You only store a hash of it, which is not reversible. So the idea is that it's secure and safe. Similar thing happens with credit cards. There's something called a credit card hash. And this is something that's very common, and most reputable businesses that run a smart program will program this properly. Oftentimes you see people get hacked and you find out that they didn't follow this proper protocol. That's where you end up having corners cut, or people that don't quite understand how security works with the internet. But anyways, that's enough of understanding how one-way hashing works, but it's critical to understand how blockchain and its underlying mechanisms and programming works. So in blockchain, you have two people for a transaction, Eric and Linda. Eric has something called a public address. Just going to shorten it to public ADR. And we're going to call it 123. And Linda also has a public address. We're going to call that 456. And Eric has a private key. We're going to call it ABC. And Linda has a private key. ABC. Now, something important to note is that same thing with houses. A key belongs to an address typically, or a key belongs to a house. And so these are related. This private key is related to this public address. But something important to note is this is what goes on the transaction, the public addresses. So if I pay Linda $5, the transaction will read 123 paid 456 $5. And then after it, there will be something called a hash. So a hash up here. So the transaction will read like this. And that hash is where the magic happens. This hash is what is used to verify that the transaction is valid. So in order to verify that this hash is correct, in order to make sure that this is a valid transaction that was not forged, all I need is the public address for both of the recipient and the sender. And I can say, oh, well, yeah, that's a valid hash. But remember, hashes are one way. So I can't generate a hash with just a public address, is an important thing to note. In order to generate the hash, I need the private key. So this is a really cool, complex thing that I think is beyond the scope of this video. But a hash can only be generated by a private key, but it can be verified with public keys. It's kind of a weird concept. Mathematically, it's really crazy. But the idea remains. If I keep my private key private, as the word is, it means private. If I'm the only one that knows my private key, I'm the only person that can sign this transaction, because I'm the only person that can generate a valid hash. And this hash involves information. It takes information like the dollar amount and the address for both. And remember, it's not reversible. So if I keep this private, I'm the only person that can generate this hash, but anybody who sees the addresses here can verify it. So now we have this public ledger that has public information and everything about every transaction and can be verified by anybody. But the only people that can write to it and have valid transactions are those who have their private keys. So this is often known as a private address or a wallet private key. But the idea is that as long as I keep that secret, as long as I keep that safe, I can protect my money. Now, some other cool stuff with Bitcoin or blockchain is it's not just individual transactions. Because in blockchain or in Bitcoin, there is no back-end bank that you can say, oh, Eric paid $5. Can we check the bank to see if Eric has $5? There's no database to check. There's only this line of transactions. So rather than just have that, you actually just have this very, very long pathway of money. So at the very beginning, if I create my address, we're going to call my address E123. If my address, I bought Bitcoin. So some mysterious person who already has Bitcoin sends money to E123. And he sends, let's say, $10. E123 now has $10 that he can spend. If E123 were to try to spend $15 and send it to Linda, this when it's verified by the public, which again, anybody can do this, they would be able to see, oh, hey, Eric doesn't have the funds. That's not a valid transaction. It doesn't go through. It gets rejected. So the idea behind this is not only are the transactions individually verifiable that Eric has created this transaction, Eric is the one who's saying I'm sending money to Linda, but it also serves the purpose of checking to see that I have funds. Now, how do Bitcoins actually get into a person's wallet in the first place? How do they enter this transaction window? It's something called mining. That, I think, is outside the scope of this conversation. But in theory, there's really complicated math that works out where you can actually spend computing power to generate Bitcoin. And that also has the side effect of verifying all the transactions with the hash. So with this ledger, there's currently no incentive for everybody to look at and say, hey, are all the transactions valid other than being a good Samaritan? But when you add in the idea that if you make money for doing that, which is how it works today, you make money for verifying transactions. And so that's how money enters the ecosystem, is that verifying transactions itself actually has a benefit of generating money, as well as you can also put a fee for verifying it and take money out of the transactions too, and that's a whole other thing. But anyways, the idea behind this is not only does it verify that each transaction is legit, it also checks your balance. And so that's the gist of it. Now the last bit is that rather than having a single place where the ledger lives, so there's not like a single server where everyone goes and peers into and checks, the ledger lives on a network. So you have, let's say, 10 computers. Or let's do 9 computers because it's prettier than having a random node out here because that just looks ugly. There are 9 computers as a part of the network. In reality, there are way more than that. But when somebody makes a transaction over here, it goes to all 9 computers in the network. In theory, it sends to all computers in the network that are watching or managing the ledger. And it doesn't necessarily have to send to all of them individually. These are actually in their own network, so they'll communicate with each other and send it to each other back and forth. But what ends up happening is when Eric makes a transaction, it goes to all these computers. They all individually verify it. And if the majority of them verify it, then it goes through and the transaction is valid. Now, what happens if the majority of them don't verify it? Well, then it gets rejected. So if you're astute, you might notice there's potentially a problem here. What if somebody is able to take over more than half the computers? What if, for some reason, some random government, a malicious government, let's say the US of A, that's a joke, but let's say the USA decides to create their own set of nodes, which, by the way, anybody can join this network. This is a public, the way that this works is anybody can join it and anybody can be a part of the verification strategy. And so you could add yourself here as another node and be a part of the network immediately. But the idea here behind this is if you don't exist down here and the majority of these belong to a single entity, the majority of these could halt transactions. They could just reject everything. Or they can do some other nefarious things like something called double spending, where you could spend the same money twice and then it really causes a lot of problems. Now, in reality, because if this ever happens, it becomes very clear and very apparent that there's some fishy business going on, and that immediately would say, hey, you know what, this is not valid, shut it down. Everyone would go, okay, you know what, Bitcoin's kind of a mess right now. It's not, let's hold our horses. They can't just steal money because, again, they don't have private keys. They can't steal your money. But they can halt the transactions. They can take the whole network hostage. But money doesn't just disappear. It freezes. It's kind of like a freezing of your assets. So that's really the big threat to Bitcoin right now, is if somebody can get more than 50% of the network of verification, they can own the net. They can take the network hostage and maybe do some nefarious stuff. It's something called a 51 attack or a 51% attack. It stems from the idea that if you have more than 50%, aka 51% of the network, you can attack it fairly easily. But one, this requires such a ludicrous amount of computing power. It's not reasonable to assume that any one person can do this. And two, it would cost you way more money to do this than the money you would potentially gain by taking the network hostage. You could potentially double spend and make some of your money back. There is some cases where if you had that amount of computing power, you could potentially do it. But if this were to ever happen, the value of Bitcoin would just plummet so much that there would be no point in stealing the Bitcoin. The only way you would make money is by making like hedging against Bitcoin, at which point it becomes very clear. Hey, you borrowed, $30 million of money and you said you were going to pay it back in Bitcoin to the bank, and all of a sudden Bitcoin's worth nothing and the bank's going to get pissed and you're going to have a lot of people after you. But anyways, that's kind of Bitcoin as a whole. There's obviously some stuff in there that's a little bit more technical, a little bit more complex. I'm not entirely familiar with all of it either, but hopefully this was informative and hopefully you enjoyed learning about this. If you have any questions, feel free to let me know. Otherwise, I enjoyed making this, and thanks for watching. Have a good day.